Wait. Yeah. Start.
So the next talk will be by Anirban on the topic best term identification in rarity.
Hi, good evening, everyone. So this is basically some original work that I did with Sushant and Sanjay. So let's proceed. So the outline of presentation is something like this. We'll briefly introduce what best term identification means, what rare event means. Then we'll take a look at generic framework. Then we'll look at the lower bound on certain kinds of best term identification algorithms. Then we'll take a look at a family of algorithms that matches the constant of the lower bound. I mean, plus some lower order terms, but by and large matches the constant. So this family of algorithms has the drawback of being computationally very expensive. And this computationally expensive thing becomes a huge problem when we are in the rare event framework. So what we are going to do is, in the rare event framework, we are going to introduce some approximations, use them and run very similar drag and stop algorithms. And we are going to see that now computationally we have become much more efficient with a small price to pay. And additionally, our approximation also gives us certain structural insights into the nature of this drag and stop algorithms, which we'll get into if there is time towards the end. All right. So let's jump right. Multi-armed bandits is something most, if not everyone here, is familiar with. It's basically decision making under uncertainty. There will be a bunch of probability distributions we are supposed to be sampling from, and yeah, I mean, this is a popular framework that is seen in various fields such as clinical trials. You see them in this is a casino slot machine. I'm sure everybody is familiar, but and then again, the last one is an ad, one of the various ads that we get to see on social media or elsewhere. The point is, in each of these cases, in the first case, we kind of want to decide which drug is the most efficient within the fewest number of trials. We want to decide which slot machine has the highest expected reward within the fewest number of samples. We want to decide from the seller's end, we want to decide which ad will result in maximum profit for the seller. So we are assuming that any given point of time, we can only sample from one of k given probability distributions. Henceforth, we'll informally be calling these distributions as arcs. Okay. So let's get a bit more formal. So the k probability distributions we are going to denote by P1 through Pk. The objective again is sequentially, we will be sampling from these k distributions as per some scheme. And after stopping, we want to say that, okay, such and such arm is best with the probability of 1 minus delta. Best meaning that the arm with the highest expected reward. So the algorithms that can declare the best arm with probability at least 1 minus delta, we have a name for them. They are said to be delta correct. Now what we want to do is, for delta correct algorithms, we want to minimize the expected number of samples. So we want to declare, I mean, given a preset confidence level, we want to declare that such and such arm is the best within the fewest number of samples that we can. Right. And as far as rare events are concerned, so the basic idea is as such. I mean, we were highly motivated by the example of ads that we saw. So what happens is each ad that gets shown has a very low probability of getting clicked and then a sale being made, right? It is also the case that, I mean, lower the probability of making a sale, higher the reward once you do make a sale. So in this ad, there is a t-shirt which is a common product. Even selling this can be a rare event, but compare this to something like maybe a luxury watch, right? So what happens is, in the case of a luxury item, even though the probability of making a sale goes down, once a sale is made, the reward is very high. So this was our motivation. So as you can see, each arm has high probability of zero reward and low probability of a positive reward that can be very high. So again, this we can model this as a bandit problem, because basically we want to do, what we want to do is kind of show a certain number of ads and very quickly decide which ad is likeliest to result in a sale and thereby earn us money.
What is formally what is the bandit problem? Formally, what is a bandit problem?
Given these k probability distributions, at each point of time you want to sample from them, from one of them. You keep sampling sequentially at one point of time. So this is best arm identification problem within the multi-arm bandits framework. So as quickly as you can, you want to declare that a particular arm is the best, and you want to say that with a confidence of at least 1 minus delta.
What is optimal arm? What do you usually mean about
The optimal arm, by optimal arm, I mean the arm with the highest expected reward. That's all.
what do you usually mean about this? So this is system is harmonic.
Yeah.
It is harmonic.
I'm sorry?
The distribution.
Not necessarily.
Don't say anything about that.
Okay. So how few samples can we possibly take? The answer is kind of pointed towards by the data partition inequality. So we, by given a delta, we denote by tau delta the random time at which a delta correct algorithm will stop. And the data partition inequality kind of makes sense here. This log 1 by delta is the approximate KL divergence between 1 minus delta and delta, which comes from the probabilities of our the declared arm being actually the best versus it's not being the best. And the V star P basically is the KL divergence kind of quantity between the actual distribution and or should I say between the actual bandit model and the kind of bandit model that we suspect will confuse us into believing that wrongly believing that a certain arm is optimal when it is not. So this V star P expression is as follows. In between, so because we have most confusing distribution, so we want to kind of infimize over KL divergence of alternate distribution. So you can see for K in P1, we are assuming, by the way, that arm 1 has the highest mean, arm 2 the second highest, and so on. So in case of the best arm, we will be misled into believing that it is not the best when the mean is, when we are seeing a lesser mean than its actual mean. In case of suboptimal arms, we will get confused if we see, okay, this greater than has got suppressed, but we'll be misled into believing that they are optimal when the mean we are seeing is higher than the actual mean. The empirical mean that we see is higher than the actual mean. Right. So, this is the intuition behind it. Yeah. So how do we actually go about doing it? Here is the, this is the point where we see the significance of this Maxwell problem, the lower bound problem as we'll be calling it. So first, of course, also the name Drakenstock. So we keep sampling from the arms. There is a predetermined batch size, which we agree upon. So after every batch, what we do is we have an empirical distribution, which we plug into the this problem. Instead of P1 Pi, we have P1 hat, P1 Pi hat, and then we solve this Maxwell problem, which gives us this bunch of weights, the W's. These W's are going to decide. These W's are going to decide in what scheme we are going to sample in the next batch of our samples. So, and we stop when, so at the end of every batch, we have these empirical distributions. There is an empirical best arm. So we do a log likelihood ratio test of the empirical arm being the best versus it's not being the best. And the log likelihood ratio, if it exceeds a certain threshold, then we say that, okay, we are now convinced that the empirical best arm is indeed the best. And then we declare that, okay, the empirical best arm is the best with at least probability 1 minus 1. Right. So when I say family of algorithms, basically track and stop. This is step 2 is tracks, and step 3 and 4 are obviously the stop. So track and stop algorithms, I think all of them agree on solving the lower bound maximum problem. The stopping criterion varies over different algorithms. If we look at the log likelihood ratio and the stopping threshold, so we can manipulate the log likelihood ratio into looking like that kind of an expression. K star is the empirical best arm, and typically what happens is track and stop algorithms vary on what this stop threshold should be. But the stop threshold is the focal point of our discussion. By the way, this stop threshold is from Shubhada's paper that came in 2019-20. And yeah. Okay. Yeah. Now let us see why, as I had said in the beginning, this track and stop is computationally expensive. Why is that? So to solve this problem to an accuracy of epsilon, we will require order log to the power 5 1 by epsilon many operations. Now this is this log to the power 5 1 by epsilon thing comes in with a lot of nuance, which I'll get to if there is time at the end. But broadly speaking, so the k-inf problems, they have nice dual forms which facilitate solving by just root finding. I mean, k-inf, if seen as a maximization problem, there are interesting properties about the dual variables that kind of enable us to compute k-inf by just root finding, and the root finding takes order log 1 by epsilon many operations for epsilon accuracy. Now, once we have found the k-inf, we want to infimize over this x, and this infimization will require again order of log square 1 by e operations. After we have infimized and computed the minimum over some k minus 1 or something like that, yeah, k minus 1 mini quantity, we now want to maximize over w, and that again takes log square 1 by epsilon many operations.
These operations are computational.
Yeah.
You don't really start.
No, computational operations. So that brings us to order log to the power 5 1 by epsilon. Now, what this immediately tells us is when success is rare, we need higher precision and thus lower epsilon. And this order log to the power 1 by epsilon is going to go up. So when successes are rare, so when P1 distribution, like 0 has a very high probability, but other rewards or positive rewards are very low probability, what will happen is the KL divergence itself becomes a very small quantity, right? So for solving that, we need higher precision and low epsilon. Small epsilon means it goes up. Okay. So what is the workaround? It turns out that when successes are rare, we can, so immediately rare success kind of pushes us into imagining, okay, there might be something to do with Poisson. Turns out it is the case. How? So we perform a kind of Poisson approximation, which I'll get to now. And then we see that using that approximation, computation speed gets a drastic boost. How is that? So before that, we'll need some notation. We'll say that the ith arm shows a reward once in every gamma to the power minus alpha I times in terms of order. And the rewards will look like, just like I said, right? Rarer the arm, rarer the success, higher the reward when you do see a success. So that is captured in reward of Aij gamma to the power minus alpha I, and proportionately the probability is Pij gamma to the power alpha I. And with a very high probability, you see 0. Okay. And another thing is, we are assuming that every arm has kind of order 1 mean, because I mean, if let us say in a bunch of arms there is one arm which is lower than order 1 mean, within very few samples it is going to get identified and discarded. And if something has a considerably higher mean than the other arms, that will also get very quickly identified and be called the best. So the interesting case is when all of them are kind of order 1 and the means are again. Yeah. So the Poisson approximation. Turns out for gamma small enough, the first thing that I mean, while working, we observed is a simple Taylor approximation around Pij will give us this kind of an approximate expression for KL divergence. Now, the interesting part is, I mean, this thing is the KL divergence between two distributions with two Poisson distributions with parameters Pij and Pij tilde. And there is this multiplicative factor of gamma to the power alpha I. So this can be read in the following manner that, for the ith arm, because we see a success in about every gamma to the power minus alpha I many samples. So we say that, okay, let us consider gamma to the power minus alpha I samples as one try. And now, whether or not we see a particular reward there, that becomes a Bernoulli variable, which yeah, because the probability of success is very small, it is approximately Poisson. So where does that lead us? Now, what we do is remember the K-inf expression. I mean, it will come in a few slides again, but this K-inf is an infimization over KL, right? Once we plug in the approximate KL, it is then that everything starts to happen. So before that, again, the track and stop. What we were doing, we were sampling the arms, we were getting empirical distributions, we were solving the lower bound problem. Instead, what we do now is solve the approximate lower bound problem. And again, log likelihood and the stopping rule we are not tampering with much, but just that approximate step speeds up computation drastically. How does it do that? We have already seen that the K-inf computation requires order log 1 by epsilon, and the minimization step requires order log square 1 by epsilon. It so turns out that if we substitute that Poisson approximation, the nature, I mean, the approximation itself and the first order conditions that emerge from it, that lead us into computing this entire infimization problem as one root finding exercise. So from order log cube 1 by epsilon, we have reduced ourselves to order log 1 by epsilon. The outer maximization, we do it as it is, I mean, as before. So that stays log square 1 by epsilon, but the net effect is that from log to the power 5 1 by epsilon, we have come down to log cube 1 by epsilon. Remember, epsilon is going to be very small, so I mean, the benefits, the computational benefits will be quite huge. Okay, so quickly the theoretical guarantees. TSA is delta correct. So, and the asymptotic sample complexity is, you might remember the V star P quantity, right? I mean, I have to go quite a bit back, but V star is basically that max min quantity, right? Yeah, this is V star. Instead of V star, what we have is, sorry. Because we are solving the approximate problem, we have something called VTSAP. It's an approximate solution to that problem. Now, we have also been able to prove that this approximate solution is off from the exact solution. In terms of relative error, we can see order of gamma to the power minimum alpha I, so the least degree of rarity. I mean, but in absolute terms, it is order gamma to the power twice min alpha I. So, I mean, instead of 1 by V TSAP, we could just say 1 by V star E minus some order of gamma to the power twice min alpha I. So this is the cost that I was talking about in the beginning. So with some slack towards the sample complexity to our detriment, we gain a lot in computational efficiency. So one example in detail. So suppose gamma is, I mean, it's not very small. Even if we consider 10 to the power minus 3, and let's say all the arms have the same rarity. Everybody shows some reward once every 1,000 times. So the track and stop that we were comparing with showed us the best arm in some 290,000 samples, but it took like almost 270 seconds. We did it in 330,000 samples within 27 seconds. So, I mean, like I said, massive computational benefit at the cost of a small increase in sample complexity. There is 5 minutes, so let me go to the structural insights. So, what happens is, if you see the, I mean, I'll just get back to the max min problem. There is a max to the left of it, of course, but what I mean to say is, like I was saying, solving the max min problem gives us a bunch of these WIs or weights, and these weights determine how the subsequent arms are going to get sampled. So it so happens that depending on whether the best arm is also the rarest versus whether it is not, the optimal weights kind of take on different structures. And I mean, under different scenarios, if best arm is not the rarest, we have something. If it is the rarest, then we can have different scenarios depending on whether it is uniquely the rarest or not. Now, this zeta quantity is something that comes in as a solution. I mean, while we are solving the maximization part of the problem, but we do not have a very good intuitive understanding of what this zeta is supposed to mean. However, even on the basis of this zeta, we have different scenarios. Sorry. So again, one little bit of notation again. X by X star will mean, like in the beginning, I was saying that there will be some most confusing bandit model. I mean, we are seeing the samples, but we believe that instead of the actual model, it comes from somewhere else. What is the most confusing somewhere else? What are the means of truth? So that is denoted by X star. And in the subsequent slides, seeing a positive reward, if a sample shows a positive reward, we call it an informative sample. All right. So I don't think we'll have time to examine all the cases, but suppose best arm is not the rarest. So then what happens is this most confusing distribution is closer to the highest mean. So I mean, we were optimizing, if you notice, between the ith mean and the best mean. So the most confusing mean happens to be closer to the best mean. That is the first insight. Now, sorry. Yeah. If you see, I mean, it so happens that the upper bound, the solution overall is going to be order of gamma raised to minus alpha max. So if you multiply minus gamma raised to minus alpha max, you get to see that for every arm we are seeing about order 1 informative samples, but for the best arm we see a bit more of informative samples. So I mean, the intuitive explanation that we can see behind this is because best arm is not the rarest. I mean, within those many, it will supply us with more informative samples, and we'll be quicker to ascertain that it is indeed the best. Similar kinds of arguments actually work in all the other scenarios, but since I'm running out of time, I guess I'll stop here. Any further questions? Thank you.